All right, so we are right at the start time of 2 o'clock Eastern Standard Time, so we'll go ahead and begin. First off, good afternoon. Once again, I'm Jason Thomas, project engineer at America Makes, and I'll be your host for today's America Makes TRX webinar series. A little background on the TRX webinar series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium called the America Makes Technical Review and Exchange webinar series was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with the broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief question and answer session. If during the presentation you do have a question, please submit it into the chat space on your team screen, and I'll ask it during the Q&A session. I will do my best to get all of your questions answered. Today's webinar is on end-to-end manufacturing service by FasTech, LLC. Without further ado, it is my pleasure to introduce excuse me, Yash Bhandari of FasTech. Excuse me. Dr. Yash Bhandari works at FasTech Engineering as a director of business development. He is an internationally recognized manufacturing professional who has more than 12 years of experience in directed energy deposition DED processes. He is one of the few individuals in the world to have experience with all the three heat sources, arc, laser, and electron beam in AM at reputed organizations in the US, UK, and in India. His current role at FasTech involves providing AM solutions to clients and managing AM projects. Prior to joining FasTech, he worked at Aditech Meltio as a business development manager. He received his PhD from Cranfield University in the UK. He also gained experience working for Tata Motors Limited, Oak Ridge National Lab, and Edison Welding Institute. He published several articles, chaired various conferences, and gave numerous talks on AM. He's an advisor for SME and actively participates in ASTM F42 Committee and an ASM International Emergency Technologies Committee. Yash, I will now turn it over to you and your team.
All right. Thank you very much for the introduction. It's actually overwhelming. All right. Good afternoon, everybody. Thanks for taking the time and joining in the webinar. I'm really excited to be presenting about FasTech Engineering, who we are, where we are, what do we do on a daily basis, are some of the points that would be covered during this presentation. But first of all, we are proud to be members of America Makes, and we are really looking forward to be involved in America Makes activities. So without further ado, let me jump straight into the presentation. So this presentation won't take more than 35 minutes. Okay, thanks, Jason, for covering about me. So who are we? So where is FasTech Engineering? So we are a small business company based out of Danville, Virginia, founded in 2018. So roughly 5-year-old company. And we're not far away from North Carolina state borderline, like 5 minutes we drive and we hear on the map saying, welcome to North Carolina. We're about 5,000 square feet facility, and very soon we will be expanding to 30,000 square feet. It's in the same campus. The campus is expanding, and we're proud to say that US Navy's AM Center of Excellence is also in the same campus as we are right now. So this gave us a lot of opportunity to work with US Navy and qualify, print, and the end goal is to print parts, and manufacture parts for them. So it makes us a big deal to be in the same campus, as with US Navy. We're a small business company, and we're about 15 to 20 people. We are on a upward trajectory. We're always looking for people. So if you know anybody or if somebody is looking for jobs, feel free to contact us. We are an internationally recognized company. We have customers all over the world, but primarily based, out of the US. We are proud to call ourselves as end-to-end service provider. So what exactly is end-to-end service provider? So there are a lot of manufacturing steps that are involved to manufacture a component, right from CAD model to the final finished specs required by the customer. So we undertake all the important items that are required for manufacturing the components. So we have three main verticals. The first vertical being the additive, the second vertical being the CNC machining services, and then third and not last but not least is reverse engineering and metrology. So, in my opinion, all these three verticals are important to create a component cost effective. And these are all important steps, even in general manufacturing, production line as well. And we also do project management on the NDT services, just because on the background of, a lot of individuals who come from the NDT world, actually. So we combine additive, machining, and then metrology, to manufacture a component. That is why we would like to call ourselves as end-to-end service provider. So we do only additive. In some cases, we just do only machining, or we just do only metrology as well. So we have customers, who come from all these three different backgrounds. So that is why, FasTech is proud to be called as one-stop shop solution provider. Okay, getting more into the details. We are an ISO certified company. Since we work with a lot of aerospace companies and federal government company organizations, we're also ITAR registered, company. Not to digress too much, but one of the things that we are really proud is that we are a part of AM Forward initiative. But those who are not aware of this initiative was started in 2022, towards the later part of 2022, and started by the federal government itself. So the goal of this initiative is to encourage large companies to work and source additive manufactured parts from smaller companies like us. So in this picture, I'll not go too much in details. In this picture, you'll see our CEO, Alan, who's at the center. And to his right, you see Siemens. And then on his left, we see the president. So this picture was taken at AM Forward Initiative, back in 2022, Ohio. And, so this is one of the great examples how large companies like Siemens, work with, smaller companies, like us. These are a couple of components that were showcased to the president. Okay, in terms of our customers, one of the things that we are really lucky and proud is the diverse background of all of our customers. That just shows, what additive manufacturing can be applied, or where manufacturing can be applied. It's versatile. It can be applied in energy sector. It can also be applied in naval sector, aerospace. They're one of the forefront runners, automobile sector, tooling sector, and whatnot. So this just proves that, where all additive manufacturing, can be applied. Just the other day I was talking to a customer from food processing industry. So never ever I thought, 10 years ago that, additive manufacturing could be applied, in food processing industry as well. So what's uniqueness about FasTech engineering? So if we take a step back, so what are the bottlenecks of the current manufacturing scenario? So after talking to a lot of customers, a lot of individuals, we put forward these 5 points listing the bottlenecks. So the first and foremost, all the customers that come to us, they mention is the long lead times. Just to get a few components, in steels or titaniums or nickel-based alloys, it takes about like 9 to 12 months, with these conventional manufacturing processes. So we all know that machining, casting, and forging, they take up like at least 90 to 95% of the manufacturing processes. And especially casting, the lead times are pretty much killing. That's what people, customers quote. Some of the small scale components or the one-off components or a low batch components, they take as high as like 9 to even 24 months. So this is not the best scenario, from a manufacturing standpoint. And because of COVID, the prices are also getting very high. And then we all know that for the last 2 to 3 years we have been seeing a disruption in supply chain, and then transportation problems. So how can you print or how can you manufacture component in an oil rig, for example? So all of these things put together makes us believe that additive manufacturing is a solution that can mitigate the current manufacturing bottlenecks. So why additive manufacture? Additive manufacture, I mean, as we all know, that you print a part using layer by layer. So the initial requirements could be powder or wire. The requirements are very low, as opposed to casting, where you have to have a mold, prepare mold. So I think just as a starting point itself, additive manufacturing is a viable solution. So you'll not have any transportation problems, or the supply chain issues will also be a lot mitigated. So that is why we thought and we think that additive manufacturing is a viable solution to mitigate those bottlenecks. Again, under metal additive manufacturing, there are a lot of processes, right? I broadly classified them into two types. One is powder bed and then DED processes. And as we all know, powder bed is a lot more matured compared to the DED side of it. However, we are seeing a big gap in manufacturing large-scale components. So this is where DED processes, directed energy deposition processes, come into picture. They're not as old as powder bed fusion processes. They're relatively young, I would say. Although it was started at least like 20, 30 years ago, but a lot of traction was developed during the last 5 to 8 years. So it is still in the low to medium TRL level, I would presume. So this is where we want to create an efficiency. We want to fill the gap and help manufacturers build components in a more cost-effective way. So even under powder DED and wire DED, you change the feedstock, you would get two types of techniques. And we think that wire DED is better than powder because of a lot of reasons. As we all know that in wire DED, 100% of the material is utilized. And then the deposition rates and the productivity are at least like 10 times higher when you compare with powder DED. So all these reasons, drove us to pick wire DED as opposed to powder DED. Of course, powder DED has its own place. You have a wide, selection of alloys. You can create your own customized alloys. You can create very fine features. But we wanted to pick a niche area where we want to concentrate on large scale applications, where the lead times are as high as like 9 to 12 months, and the deposition rates, which are not high in the case of powder DED. And not last least, even the safety aspect. The wire is a lot more safer compared to powder. And the point is the properties as well. So you don't need to do a lot of post processing with wire as opposed to using with powder bed fusion or even with powder DED. So this is a holistic approach that we took 5 years ago, and so that's why we apply wire DED and then combine it with machining and then inspection. So even under wire DED, you change a heat source, you would get a new variant of wire DED. So that is why we have two technologies under wire DED. The first technology is wire arc additive manufacture, WAAM or arc-DED. And then the second technique that we use is laser metal deposition or LWDED in short. And then it's no brainer that everybody knows that the parts that come out of wire-DED systems are a little rough, about 250 to 500 microns surface finish. So it's always required to do one final finish machine so as to get to the right tolerances, required for the part to, fly, for example. So yeah, so we apply wire and then we use wire and then apply it in one of those two systems, depending upon the part dimensions, depending upon the material, depending upon the end use. So a part will go, into one of those systems. So that is why we consider these two systems to be complementing each other rather than, fighting for each other. They're not competitive, but instead complementing. And then the last step being, the machining operation. So I was saying who we are, but what's the uniqueness of working with FasTech? So why work with FasTech? Why FasTech services? As we all know that the DED systems or generally additive manufacturing systems are expensive. I work personally on a 500K system to even 3 million, dollars machine as well. And this is not it's a bread for everybody, right? Bread and butter for everybody. So that is why we have this system. So you don't have to invest in them. Instead, it just print, parts out of them. So we have skilled personnel. We have decades of DED experience. A lot of people come from the oil and gas industry. We have people coming from machine tool industry. So that is a very good mix and match. Because all these are important to get to the final part. And we're proud to be associated with a lot of projects where we learned, and now we are able to call ourselves as experts in process parameter development, DFAM side, we can create business case for parts and validate the technology. So we can print one part or even like hundreds of components. So we have customers who just ask us to print just a small part. On the other side, we print production parts for a lot of customers as well. We deal with a lot of materials like steels, titaniums, nickel-based alloys, aluminum alloys, copper alloys, or you name any alloy that is available in the form of a welding wire. It can be applied, on our systems. And we always conform to ASTM standards. So this is where our customers like us. So we understand them, and not just from a printing standpoint. We also understand it from the post processing, the heat treatments, the surface finish standpoint. So every different sector has their own requirements, and we understand them and then apply during the manufacturing processes. And QA and QC are of topmost importance for us. So back to the technologies that we use at FasTech. So we apply two technologies, WAAM and LMD wire. The WAAM technology is powered by Tech. It's a German brand, and it can print, as you can see, it's a big machine. It can print, up to meter-long components in all directions, both 3 axes and 5 axes. And then on the other side, on the LMD wire side, we have a system coming from Aditech Meltio, where we use robotics, and it can also print up to 1 meter long components, but in fact 1.8 meter long components. Most of the components that fall, most of the components that we get from customers are about 200 mil to 800 mil. So, but there's a lot of room that can be printed in these systems. So for us, both of these systems, we invested in both of these systems so that we can provide a cost-effective solutions, to the customers. So if there is a part, in order to be cost-effective, it'll only go in one of these systems. If the part goes to both of them, if the cost is same, then I think it's not a great fit to wire-DED in that sense. So In the next few slides, I'm gonna introduce you to the WAM technology and a couple of case studies on both the sides of the technology, and then how do we differentiate which technology goes where, which material based on materials or dimensions. So all of those things will be presented in the next slides. So first up, WAM process. So as we all know, WAM stands for wire arc additive manufacture, where we use an electric arc and then combine it with a gantry system or a robotic, and then use wire to print these components. So in this video, you see in this video, you see the printing process using WAM process. So we can so this technology, so this system can print using 3 axes and also 5 axes, um, not just steels, but also highly reactive metals like titanium as well. So it has an argon chamber which can get down the oxygen levels as low as 50 ppm, which is very good from an aerospace standpoint. So here we use CMT as the power source, and then combine it with the gantry system because the gantry systems are more robust, compared to other forms. And then and then CMT, a gantry system, and then wire, and then they all combine to give the WAM system. So we also incorporated sensors based upon our background, where we come from, and then we use the pre-existing welding standards to print these components. And then um, on the other side, laser metal deposition with wire, we use robotics as opposed to gantry system. So the reason why we use robotics is it's because of its flexibility. As we all know, a robot has 6 degrees of freedom, and then if we incorporate a positioner which adds 2 more degrees of freedom, essentially it gives 8 degrees of freedom, and that just shows the versatility in terms of geometries that can be printed. So just this example itself, it would have been near to impossible to print using 3 axes. So making use of this rotary table and then the 6 axis robotic system is important to make these type of components. So as the name says, laser metal deposition. So laser is the heat source, and then wire, and then robotic system. So all these three combined will give laser metal deposition with wire as the process. So there are two different heat sources that we use. On the WAM side, we use electric arc, and then on the laser metal deposition, we use lasers. So that's the first and foremost difference between these two technologies. So you change the heat source, then the whole dynamic changes, right from the melt pool, to what type of materials that can be employed, and what will be the properties, and all of those things are all important. What I call as to the success of manufacturing a component. So what are the differences between our WAM system and our laser metal deposition system? The good news is both can print meter-long components. We rarely see 2 meter long components, but we still use it in a more effective way if we are to print multiple components in a way. So that's good. And in terms of multi-axis capability, both of them can do just 3 axes, just 3+2 axes, and 5 axes as well. So for example, like impeller, if somebody wants to print an impeller, I think 5 axis capability is important. And, both of the technologies are capable of doing. So on the other side, one of the cons from WAM side is the minimum feature size it can print is about 6 millimeters, about 5 to 6. But in most of the scenarios, it is 6 millimeters. On the other side, lasers can print even finer features, starting from 2.5 millimeters. So why there's a difference, you might ask? Well, it's all about the deposition. The deposition rate is completely defined upon how much material feed rate you use, how much power you supply to the wire. So more power you supply, more material can be deposited. So in that case, you're printing or depositing thick features as opposed to printing thin features. And then, as we all know, that lasers have a spot size. ranging from a few millimeters to, few nanometers to few millimeters. So this is one of the reasons where you're able to concentrate the heat over, a small area. And this is which in turns give high precision and then low feature size. And then in WAM, there's no heat, spot size. So the heat source is pretty much, convergent. So that is why you would see, thick features as opposed to thin features in laser metal deposition. But on the other side, one of the big pros, from WAM standpoint is, not all geometries are thin. We come across a lot of thick geometries as well, more than, 6 millimeters. So in that case, we use the maximum capability of our WAM. So the productivity when it comes to WAM is very high compared to LMD process. It's more than 10 times in terms of deposition rate. 4 to 5 kilograms is our typical deposition rate, on a daily basis, as opposed to, 0.3 to, 0.25 kilogram per hour as the deposition rate when it comes to laser metal deposition. So it's clear that if the part is big, if the part is thick, then we apply WAM process. And then if the part is small, or if it is thin, then we would employ laser metal deposition. A lot of companies, they just do either additive or subtractive. Since we deal, these two processes under the same roof, that is why we also consider that not just printing, but the subtractive side also needs to be thought about, because you can print 6 millimeters Inconel, but then if the final component is only 2 millimeters, you have to remove 4 millimeters, using machining process, which is a very tedious process, when it comes to alloys like nickel-based alloys and titaniums. So these alloys, they're very difficult to machine, and they're very expensive too. So you don't want to waste too much of material. At the same time, be more cost effective. So that is the reason, if somebody asks, why do you have two wire-DED process? So this is the reason, why we have two wire-DED processes which complement each other. And on the WAM side, you have more options to play with. As you can see, steels, titaniums, and nickel-based alloys are common to both these processes, but aluminums and coppers, because of their high reflectivity and poor absorptivity, WAM process is a great fit for these two materials. But essentially, any material that is available in the form of welding wire can be applied, in either of these processes. And then the max, weightage of the component that can be manufactured, is 3 ton. We rarely see 1 ton, but it's good to have these capability, because when it comes to the high density alloys, you can easily catch up with the weights. So based upon the pre-existing welding standards, we have sensors, the state-of-the-art sensors, which monitor and record and give feedback literally every microsecond, every millisecond. So this is where our background in welding engineering comes into picture, and then we are able to capture them and then do judgments in case of any anomalies. And then the last point about these two processes is, both of these processes employ coaxial wires, which is a big deal break, because if you have the wire coming from side, in for example, plasma or in other forms of wire-DED systems, the tool path generating the tool path becomes a big headache. Controlling the melt pool becomes a lot more difficult. But in the case of coaxial wire, since it's symmetric, controlling and then manipulating the melt pool becomes a lot more easier. So this is a workflow. It's not a typical workflow what you would see with a additive company or a machining company, since we employ both of these processes, and then we add this inspection element as well in the workflow. So that is why it might look a little different. So for every part that we manufacture, we start with the CAD model. We print them either on WAM or on the LMD system, and then we scan them. So the reason why we scan them is we got to validate the geometry, and not only to validate, that scan model will actually act as an input for the CAM side, which is the machining side, and we're able to create tool paths from the CAM standpoint as well. I'm going to show you a few case studies that we are really proud of working with a lot of customer applications. So a lot of components that I'm going to be showing, they are real life engineering components rather than any prototype components. So please pay attention and feel free to ask any question at the end of my presentation. So the first part is an nickel-based alloy Inconels 625 component. As you can see, Siemens component it is. So this is one of the biggest components that we made. As you can see, it is 850 millimeters in diameter. And I say this point to everybody that there are 1,000 different ways to manufacture or to print a component. But there'll be only a few cost-effective ways, where you're able to print the geometry very close to the CAD and also attain good, mechanical properties. So we employed two different strategies. The first strategy is basically print everything, literally everything. Start off with a substrate and print, the ring and then, the features on the circumference. The second strategy is we use a rolled plate and then we add these features. So out of these two strategies, we found out after doing a lot of R&D that the second strategy is more cost effective compared to the first one. So this is a video of our printing where it shows we already started with the roll plate and then we are able to add these features the circumference. So I know this is a fast forward video, but one of the things what we creatively applied is, again, even in terms of printing the features, tool paths and then the AM software are all important. So what we have done creatively is to mitigate any distortions, if any. So we printed these features on symmetrically. I mean, so if one feature was deposited here, one layer, so the next layer was deposited here. So and so on and so forth, so that there will not be any distortions. So all in all, the print time took up about just 4.5 hours, and the machining time took about 3.5 hours. So as you can imagine that nickel-based alloys, they are slow to machine. So all in all, in about one shift, we're able to print one component, right from CAD model to final finished component. Another component in stainless steel, moving from nickel to stainless steel. This is still one of our biggest component that we are really proud of. It's an aerospace component, bell mouth, and here this took about 45 hours, including cooling time. As you can imagine, even with 4 kilograms per hour, we are able to print it in 45 hours. So think about using powder bed or of course powder bed, it will be very difficult, but even with powder DED or low deposition AM processes, it would have taken like hundreds and hundreds of hours. So in this for this part, we employed 3 axes, 5 axes configurations because of just the geometry itself, just the overhangs that need to be considered. The typical aerospace component. So the reason why I'm showing you this component is so you can see how the final finished surface looks like. A lot of people, when you see this as printed component, you don't know what are the defects that might be present. But once you final finish machine, the defects, the pores and all will be clearly will be clearly visible. So this is where we spend a lot of time to refine process parameters and then lock them down and then use them during the printing process. So all in all, it took 16 hours to both print and machine. Another real life component, it's an automobile component out of stainless steel 308. So one of the things that I would like you to concentrate is, the savings. So using the conventional process, the total cost is about 5,300. Using WAAM process, it's about 2,600. So it's a little more than 50% savings. So as we all know, stainless steel is not that expensive, but think about if the material was nickel-based alloy or titanium, so there would be massive savings, massive reductions in buy-to-fly ratios. So this is where, our DED processes, will come into picture and then provide a most cost-effective solutions. At the same time, we have been seeing a lot of companies pushing, to reduce the carbon emissions too. So all of these things are important, for reducing the carbon emissions. My favorite alloy is titanium. This is also a real life, aircraft component, and it's for one of biggest aerospace companies in the US. Um, I'm really proud that we were able to print and machine within 12 hours, actually. Um, so a couple of innovative things that we applied while printing this component is we actually um, incorporated this build plate into the final component. Since we can do both 3 axis and 5 axis rotating the tilted side table too. So that is why we are able to print on either side, go back and forth after every layer so that the distortion is mitigated. So the main reason why we incorporated this technology is just the geometry itself. So it's just a geometry which will define, what strategy we will use for printing the components. So based upon looking the strategy and to provide a more cost-effective solution and to reduce the amount of machining or the post-processing required, this is one of the creative ways to print this component. So our software, will be able to create the toolpaths to print on the both sides of the build plate itself. The best part about incorporating build plates is we don't have to worry about defects because they're all like wrought quality, and we don't have to worry about the properties inside this build plate. So all in all, I also want to touch base upon, the discoloration. A lot of components that I see, titanium components especially, you would see pretty much like rainbow colors. Every color you would see while printing. So it could be mostly during oxidation, but it could also be it could also be due to heat accumulation. Since we use pre-existing welding standards, we don't put too much of heat, between the layers. So that is why you're able to see it's just one color and no, discoloration, that you would see with, a lot of titanium components. And of course, all the titanium and all the reactive alloys, they're all printed within a nice argon chamber, which can get down to oxygen levels as low as 50 ppm. Last case study. So this is on the LMD side. So the reason why we like LMD is I can print very thin features. When somebody looks at the final finished component on the top right corner, nobody would believe that this is a hollow component. But because lasers can print very fine features, we are able to print this hollow components and then close the hollow into a solid part at the edges. So all in all, it took about 43 hours, and this is also quite large, from an additive standpoint. Okay, coming to the end of my presentation. So yeah, we deal with every material that is available in the form of welding wire. So it's just the customers who come from varied backgrounds. They have their own preferences. So lately, we have been getting a lot of requests on the aluminum side as well. So that is one of the those alloys which is getting a lot of traction. In addition to stainless, nickel-based alloys, and titaniums, we have qualified a lot of materials. Qualification as in not just printing a block and then taking a couple of samples, but evaluating everything right from hardness to all the mechanical properties involved to microstructure. So this is an ongoing project. So if somebody's interested to know more about this, please let me know. I'll be more than happy to discuss with you. Another capability that I forgot to mention is multi-material printing. So what I mean by multi-material printing is you can manufacture a component that will have different mechanical performances at different sections. So this is a great capability of our process where we can print different materials at different layers. As you can see here, there are three different materials: mild steel, stainless, and hard facing. So I still remember an example where we printed like a dome structure where the inside of the component, which is the real deal surface, was printed with the right material, and then on the outside it was printed with a low cost material. So yeah, in a nutshell, as long as those two materials are compatible from a fusion standpoint, from a welding standpoint, I think using this capability will greatly reduce the total cost and, in fact, time as well. Okay, so even from a microstructure and mechanical property standpoint, as I said, we spend a lot of time in developing and refining the process parameters for printing these components, and we always conform to the ASTM standards on the defect validation or on the microstructure and mechanical properties. Okay, so to wrap up, FasTech is a company that does end-to-end manufacturing, right from additive to machining to inspection. So all of these processes are important from a manufacturing standpoint, and they're all dependent on each other. They're not like all independent. Sometimes we print, we scan, and then we go to machine, and then again we scan, and then we again go to additive. So it all depends upon the geometry of the component. Okay, so this gets to the end of my presentation.
All right. Well, hey, thank you, Yash. Great presentation, very informational. We'll now go ahead and head into the Q&A session. So if you have any questions for Yash and you haven't done so already, please go ahead and type them into the chat box. I do have a couple questions here to get started with. So we all know that qualification is a big deal. Have you qualified any of these materials that you've talked about today?
Yes, absolutely. We qualified titanium alloys, a few titanium alloys, titanium 64, titanium CP2, as a part of our involvement with Navy and other aerospace companies. Yeah, in terms of qualification, I think this is the most commonly, and it's a big buzzword right now, in additive manufacture. So is it like qualifying the process, or is it qualifying the material? Qualifying the additive system as well. So which is important actually? So I guess all are important, but people who come from a specific background, they define which is important for them, and we pick them, and then we do round robin study, print a lot of samples, take a lot of coupons, and then test them right from chemistry standpoint. We validate the printing chemistry is same as what we get in the wire form. We look at the hardness, we look at the fatigue properties, we look at yield strengths, elongations, ductility, all of these things which are important for the product to be qualified by the customer. So yeah, to answer your question, a lot of titanium alloys, and currently we are exploring nickel-based alloys and steels as well. If somebody's interested in working with us in terms of qualification, I'll be more than happy to discuss. We're always looking for partners. Sometimes we do cost share. Sometimes because it's important that this data needs to be published. So if somebody needs any part, we are more than happy to work with them and then undergo this qualification process.
Great, thanks, Yash. Yeah, definitely. We definitely need to have access to that. That's why we do a lot of the work that we do here at the Institute. So definitely see that's important. All right, so let's see. Got another one here. So we saw you talk about the two different processes that you have. So how do you decide, if a part ends up getting printed via the WAAM process or via that LMD wire process?
Yeah, that's a great question. As we all know that WAM process is very good from a deposition rate standpoint, and also, manufacturing thick components, like the minimum feature size, would be around 6 millimeters. So if there's a component other than aluminums, let's say, it can go onto both the technologies. But at the end of the day, if we want to print a component, with a more cost-effective way, if the component is very big, if it is thick, the blind rule is it just goes to WAM process. And then on the other side, if the geometry is thin, it is small, with a lot of overhangs, then we would use the robotics, which provides a lot of flexibility, and we use lasers to print them. So yeah, in a nutshell, um, big and thick components go to WAM side, and then thin and small scale components end up in LMD wire.
All right. Thank you very much, Yash. All right. So got one came in here. So in the Tie 64 case study 5, on the back side of the crank, the plate greatly exceeded the final size of the printed portions. If not only for mounting into the multi-axis machine, for what reason was it this size? Thank you.
Yeah, that's a great question. That's a great question. Um, so, like I said previously, we also think about the machining side as well. So you would need, something to get clamped to, right? You wouldn't think when you're printing, but when you go and apply it in a milling or a lathe machine turning center, then you would think, oh, okay, this is missing. So in order to reach every corner of the printed component, you would need some kind of tooling, right? So that is why we put this extra feature, so that it can be clamped, and then every other point, the tool can be reached, for the machining process. So it's just for seamless machining operation. We did, put a few more layers, and we are able to manufacture it to the final specs. I hope I answered your question.
Yeah, thank you, Yash. I didn't notice that the first time either. So yeah, Clement and asked the question. Thank you for pointing that out. That's definitely something that we don't think about that needs to be taken into consideration.
Excellent.
All right. Let's see. I think I have one more here. So monitoring is a big deal with printers nowadays. So do you have any monitoring or closed loop controls on your systems?
Yes. So monitoring is important from a qualification standpoint. Because unless we monitor, we don't know what actually are the variables that are getting into the melt pool. So there are different things that you can monitor. In powder bed, you can monitor as many as like 100 different things, but at least DED is a little forgiving. Um, so we always monitor the temperatures, because temperatures are the one which define microstructure, mechanical properties. So, so we use pre-existing welding standards, which are easily accessible, where for every material, it would state what kind of temperatures, need to be there before you put subsequent layers. So we monitor the interface temperature. We use IR cameras, and then very soon we'll be using a scanner system. So we know what's the current layer height and what's the CAD, or the set layer height, and then we make those adjustments on the either side. And then in terms of monitoring, there are at least like 4 to 5 main building process parameters that we monitor. We monitor like the wire feed speed, travel speed, and then the current voltage, for WAM process, and the argon content, all of those things, which are very important. Of course, other secondary parameters as well. But I think these all these things put together will be helpful if we were to go and then do reverse engineering. If there is any anomaly that we see at the end of printing process, now we have some data to say that, okay, this has gone wrong, and that is the result of this. So, the qualification, for a qualification standpoint, to increase the TRL levels, monitoring is it's a major it's a major point that needs to be considered for printing the parts.
All right, thanks, Yash. All right, so that's all the questions we have for today. So I think that's going to wrap up today's TRX webinar series. I would like to once again thank Yash and FasTech. Great presentation, very informational. If you do have further questions for him, you can go ahead and reach out to him directly. Yash, you want to go up and pull that last slide that has your contact information on it?
Yes.
All right, great. So yeah, you can reach out to Yash or FasTech at the email on the screen. And as a reminder, if you or your organization would be interested in sharing in the TRX webinar series, please fill out the form that follows the presentation, or you can reach out to me, Jason Thomas, at jason.thomas@ncdmm.org. Yash, thanks again for the great presentation. Everyone, thanks for joining and have a great afternoon.
Yeah, thanks, Jason, for hosting this webinar, and I would also like to thank America Makes, for giving us an opportunity to present, at the TRX webinar series. Thank you very much.
All right, thanks, Yash.
All right, bye-bye. Cheers.